and go to schedule. So I sent out an email about this, but just as an FYI, right? These are, so if we click here, right, these are the slides that we're going to talk about today, and you can see the theme is what it's been, so you know that those are updated. I have already put the slides for many other ones, but they look like this. This is the old theme. Okay, so if it looks like that, the slides have not been updated, but I put them up there just in case you wanted to look ahead. And then you can also see within here on Wednesday, we have lab 1 assigned. If you click there, you can see the actual lab, and you can look through it. You can even start working on it if your group is ready and you're ready to go. If you don't have a group yet, or you have a group but you haven't emailed me yet, please do that. And if you know that you don't have a group and that you would like me to just assign you, that would be probably easier for me too if you can directly email me and let me know that. Okay. So please email me either way, either email, this is different than what I said before, right? But please email me if you need a group, or email me with your group. If you've already done that, that's fine. That's great. No problem. But if you haven't, please do that before Wednesday. All right. Okay. So, and then Wednesday will be just a lab. So we'll be breaking into those groups that you give me or that I assign you to if you need a group. And then we'll just be working on the lab all day. Okay. During class time.
Daniel, can I ask a quick question?
Yep.
Can we assume that the days that you assign the labs will be the work day in class?
Yes, that's okay. Exactly right. So if we come back here real quick, so when it's assigned, it's up there now, right? And I'm going to try to update lab 2 here pretty soon. Homework 1 is up there already. Once it's up there, you can start working on it if you want, right? But the actual lab day where we will be in class working is the day that it's assigned. So it will be here, and this one is not in class, but lab 1 is due. And then this one, lab 2, we will be working in class on that one, on that day. Okay.
Thank you.
Any other questions? All right. Let's go ahead and get started. So today is a basic intro to visualizations. A lot of this is going to probably be review for a lot of you. But I do want to mention, before we really get into that, a note about here. Okay. So the reason, so let's do this before I do that. Can you give me like a thumbs up emoji, or just on your screen, if you feel comfortable with here, and you use it all the time and you don't need a review? And if you don't feel like that, give me like a thumbs down or something. Okay, so that's enough people that I would like to do this. So basically what I'm gonna do is, let me switch my share. I'm gonna go to just a project I have open for somebody else. Okay, so sorry, this is huge. Hang on just a second. I had some really big text that I was trying to see. So, all right. So here is, let me go to my files. All right. So this is the project directory here, right? This is, I know this is like the home for the project because that's where my .rproj is. All right. What here will do is it will always link back to that place. So if I come here and I say here, it will tell me, it will build the path basically on my local directory into this project, which is called Doug Carnine, because I'm doing some consulting work for him. Okay. So that allows me then to build these relative paths. So if I do here, data, then it will just build a path to data, right? if inside data, let's say I have another folder called raw, and then inside there, let me go put something in there real quick. Sorry, I have too many things open. So, and then inside there, I'll just put one of the other files in there. Okay, so now that file comes up. So this is dirls, that's going to list the files that are in a directory. So if I say, okay, list the files in data now, it's going to say there's this raw folder, and you can see that it's blue, so it's a folder. And then there's this EB workplace survey results, December 20th, whatever. Okay, if instead I want what's in that raw folder, then I would just say raw, right? And then it will build the path to that raw folder. The reason this is nice is because then it will always, everything will always be relative, and you can always reference everything within your directory and things won't get lost. All right, so when you're building an R project, you should always have that .rproj in your root directory. You should only have one of those, right? There shouldn't be a .rproj within an rproj. And then everything from there, every time you're saving something, so like down here, right, I saved some plots. I'm creating a directory called plots, and then inside of plots is this I did it thing. And then the plot path is plots, I did it. And notice now here, I'm actually pasting some things together. So item, whatever. And so when I do that, right, plot paths is going to build all those paths. So into plots, I did it, item 34. Plots, I did it, item 33, etc. Right? So it's going to build all of those plots. And then in this case, I'm going to loop through those paths to save every single plot. All right. So if what I would like for you to do is please always use here, okay? Because it's going to really help with reproducibility, because you should, if you're using GitHub, right? Even if you're not using a .rproj, it's going to look for that .git folder that I showed last time, and it's going to say, okay, this is the root directory, and then from there, you know, you should be able to reference anything that you want inside of that project. That also means, though, right, and this should be the case anyway, but everything that you need for that project has to be within that project, right? So if you have data, it needs to be in a folder that's in that project. It can't be in a different GitHub repo or something like that, right? Does that make sense?
Daniel, I have a question.
Sure.
So the here is used for like a setting a working directory, or like a...
No, it's used as an alternative to having to set a working directory. Because the thing that is nice about it is if I do here on my computer, it's going to build this path, right? Users, Daniel, consulting, whatever. If you did here on your computer, it would build your path to that folder, right? So if you instead, like, let's say that you shared a script with me and it says set WD, and then it has a path to your folder, that's immediately not going to work on my machine, right? I'm going to have to change that path for the rest of the script to work. And so this is a way for you to avoid using set WD and instead just build these relative paths, and it will build the full path for you.
Okay.
Make sense?
Yeah.
So essentially, but a slightly different way, you should not ever be using set WD. Okay. I linked in somewhere, I think in the syllabus, to a blog post by Jenny Bryan. I can send it out again if you'd like, but it's a whole blog post on here and why you should use it instead of set WD. Okay. It's really going to help with reproducibility, and it will take a little bit of getting used to if you're not used to using it, but it's totally worth it.
Hey, Daniel, I have a question too.
Uh-huh.
Sometimes there's the double colon to reference something out of a library without loading the library. If
Yeah,
you don't
namespace.
have a conflict between two packages and a function, what would be the reason for doing that instead of loading a library?
Yeah, so honestly, I got into the habit of namespacing here like this because there used to be a function in the lubridate package called here. And so it would directly conflict every time. And so I just started doing here every time.
Okay, so you just do it for that specific function because of
Yeah,
that.
but the
Okay.
other reason I do it a lot with janitor, for example, too, for like clean names, is because I will want, if you're namespacing like this, right, using the double colons to access a function, then you are accessing that function without loading the library. So I'm just accessing a function in the library. I'm not actually loading the library. For like janitor clean names, I might be loading one data set and I want to clean the names for that data set. And then that's it. I'm not using janitor again. So I would rather not load the entire janitor library. I'd rather just access that one function one time and then move on.
Okay,
So
awesome.
it's not like that big of a deal if you want to load both of the libraries or whatever. You know, there are some very sort of very common conflicts that you can get. So if you're using dplyr and you load the mass library, you'll see that there's a conflict with filter, right? So then you'll have to namespace dplyr filter every time, or there's a package called conflicted, which will allow you to set which ones you want as the priority, and then you namespace the other one. So there are ways around it, but those are, yeah, that's the main reason why I use namespacing.
Awesome, thanks.
Mm-hmm. Any other questions before we move on? Okay. All right. Let's go back to the slides. If I can find them. Okay. So a couple of different visualizations we're going to talk about today. We're going to basically talk about distributions, and then so histograms and density plots mostly. And then we're going to talk about visualizing amounts. So we'll talk about bar plots and dot plots and heat maps. Okay. Learning objectives for today: understand various ways of displaying the same underlying data, basically, right? And thinking through the pros and cons of each, and the basic structure of the code to produce the various plots. Okay, today, like I said, is probably going to be a review for quite a few of you, maybe all of you. But the idea is just get us sort of warmed up and get us going. All right. And then as we go throughout the term, we'll start to dig into it a lot deeper, specifically with like styling stuff. All right, so the first question you should generally ask yourself is, what type of data do you have? We'll focus primarily on standard, continuous, and categorical data throughout this class. So one of those two types, but you know, you may have unstructured data like text or images or things like that, which then you'll probably reduce into one of these two forms anyway. So that generally works. What's your purpose? Is it exploratory or communication? Because depending on which of those two things it is, the way you build plots is probably going to be pretty different, right? I would say I build probably 50 plots for exploratory purposes for every one that I use for communication. It might even be more than that, right? So if I'm just building a plot for me for exploratory purposes, then I'm not going to take all the time to do all of the styling, right? I'm probably going to set some base theme. I'm going to explore with that theme. And then when I finally get to the point where I'm ready to try to communicate some data with somebody else, then I'll go in and do a lot more modifications from there. All right, so we'll start out with one continuous variable. The basic, right, the most straightforward is going to be a histogram. And there's nothing wrong with histograms at all. They work great. They're awesome visuals, right? Density plots are probably a little bit less familiar, but they can work pretty well also. There's also empirical cumulative density functions, right, or curves. Those can be quite nice too. If you're not super familiar with them, then they're maybe a little bit more difficult, but you can get familiar with them pretty quickly as you see more of them, and then it's sort of, you're interpreting, right, how steep the line is at different points along the x-axis, essentially. There's also, we'll talk about this just briefly. This is not going to be a focus throughout the term, but you've probably seen QQ plots before with like regression. These can be nice just to use for any variable too, to see how well it approximates normality, right? So in this case, it's approximating normality pretty well because all of those points are falling close to the line. So basically this is, we're computing some empirical quantiles and comparing them to theoretical quantiles from like a normal distribution, okay? All right, I would say probably don't do this. I'm going to move pretty fast throughout the slides. If you want to come back later, you will need to install this package. And the reason I say don't do this is because installing this package can take quite a bit of time. Not the package itself, but it has dependencies on other packages, and they're all good packages and worth including, but it can take a bit of time to do the troubleshooting to install all of those. So if you need help with any of that, also please let me know. Okay, so I'm going to be using the Titanic data for this example, or these examples in this section. So this is very basic Titanic data. Basically, we have the class, age, sex, and then survived, which is a dummy variable, with 1 being yes, the passenger survived on the Titanic, or 0, they did not. So basic histogram. We have the tidyverse loaded, or we have ggplot2 loaded. Most of the time we'd probably just say library tidyverse, right? We say ggplot. We have the data set that we want to plot. And then we use AES, and we put the variable we want to display the histogram of on the x-axis, and then say plus geom histogram, and that's it. Okay. Quick little pop quiz. When do I use AES versus just putting the thing? So like, let's say I wanted to specify a color. When would I use AES and when would I not?
Does that have to do with whether we're coloring the whole thing in or the outside? I'm trying to remember from last term.
Yes. Yeah, that's close. So if you're wanting to color by a variable, or you're wanting to apply global changes, right? Those are the two different things. But what I'd like you to think about it as is AES means I'm accessing a variable in my data set for whatever it is you're doing. Let's say you're coloring, or you're doing a fill, or you're even changing something like the size of the bubbles or whatever by a variable. If you need to access a variable in your data set, access a column in your data set, that's when you use AES, okay? And otherwise you don't. So if you want to change the color for all of this thing, you do not use AES because you're not accessing a variable in your data set, right? If you want to change the color by a different column in your data set, then you would use AES, okay? So this is a basic histogram. I'm assuming you all feel pretty comfortable creating that. We can make it a little bit prettier. And so here, right, all I'm doing, notice I'm not using AES because I am not accessing a variable in my data set. I'm saying I want the fill of this thing to be this color, which is this blue color, right? And I want the color, which is now going to be the outline of the bars, to be white. And then I add alpha of 0.9. Alpha is just going to be the transparency. So this is going to say 90% solid, right? 90% opaque. All right. You might wonder where this number comes from, right? This is an HTML color code. And there's a bunch of different places that you can get this. Hang on. What's the data set I like? Go on a different. HSLpicker.com is my favorite. So this is HSL is, I think, a great way of thinking about color. I'll probably explain this more later, but basically you have the hue, saturation, so how much of the color, and then the lightness, how light or dark it is. And those are just the three components that you have of the color, right? Once you get that, you have this code down here, right? And you're just going to copy that and place it into ggplot. So that's where this code comes from to get this blue. All right. And there's a bunch of different ways you can get these colors. This one's my favorite, but there's tons of them out there. We could also change the number of bins. Okay, so notice back here on these first two, it says stat bin using bins equals 30. Pick a better value with bin width. All right, so you can use bins or bin width. They're sort of slightly different versions of the same thing. But here I've said bins equals 50. All right, and now you can see it changed the look of it a bit. Right, this is a little more spiky now. As you vary the number of bins, obviously it's going to change how it looks, right? So this is bins equals 5, 1, 2, 3, 4, 5, right? So basically it's just going to split the x-axis into 5 bins and then stack them up by how many are in each of those bins, okay? So notice this y-axis goes all the way up to 300. This one's at 75, this one's at 60. As we have more bins, the count within each bin is going to be less, right? So you can do things like this, and I think actually it's very useful to do this. Bins equals 5 is clearly not enough. Bins equals 25 is looking pretty good to me. Bins equals 50 is probably too much because now we have these spikes, but that's okay too, right? I think it's okay to look at bins equals 50 and bins equals 25 and help you get a better feel of what's going on here, okay? Because part of what I think is interesting about this distribution is that it's kind of normal, but not really, right? Like we have this section down here that's much lower than we would expect. And then you have this kind of stair-steppy thing going down this way versus like more smooth. And that is sort of confirmed over here because you have these dips, but you also have these spikes, right? So you're kind of getting information from both of those, looking at them together. This one, I think you can just throw away, but you can get some information from both of those two. Density plot. I think the basic density plot is really ugly. It's just a line, and there is some pretty good evidence that just line drawings like that don't work particularly well either. So you can make it a lot nicer looking, I think, by just adding a fill. Okay, so again, you could change the color of the fill if you want to something different, but I'm not using AES because I'm trying to make that change globally. Just change the fill to that. You could also add some transparency to it, like I did before. I like to do that because then you can see the grid lines behind it a little bit. They're not like super prominent, but you can see them a little bit. Density plots, though, are inherently quite a bit more difficult to interpret. They look nicer because they're smooth, but they use this kernel density estimation. Okay, some of you may be familiar with that, but if you're not, basically what it is it's splitting it up just like before, but then it's going to try to smooth it out. All right, so you can use different kernel shapes, so like triangle or whatever, rectangular. And then the bandwidth is what's going to matter the most. So the difference in the kernel shape almost doesn't matter, but at least for visual purposes. But the bandwidth definitely does. It matters a lot. And so if you have a really small bandwidth, it's going to bend to the data a lot, right? If you have a really big bandwidth, like way too big, it'll just look like a normal distribution, even if it's not normal at all, okay? The other thing this is the part that I think makes them the most difficult, is people always want to interpret the y-axis, right? It makes sense to try to interpret the y-axis. The y-axis on its own is pretty uninterpretable. These values are the density, and what that is if you take these values, right, and you go all the way across this x-axis and you sum these values up to there, it will sum to 1, right? So it'll integrate to 1. And so these values are sort of just dependent on the figure, and they could be totally different each time, and they're going to depend on the bandwidth. All right. So the reason that it's nice, though, is like if I wanted to say, okay, what's the probability of a value between 20 and 40, I could sum all of the values between 20 and 40, and I would get essentially the probability of values in that range as opposed to other ranges. Okay, so again, it's quite complicated. It's not nearly as easily interpretable as a histogram, but it can be nice in sort of in terms of just showing like a smoothed version of the histogram. So if you think about it in that way, I think they work really well. And if you're doing more complicated things where you need to know, like, so if you're doing Bayes sort of stuff, then this would probably be quite helpful. But in terms of just communicating, especially with a general audience, then I would be careful about density plots, okay, because they can be easily misinterpreted. So you can change the bandwidth. As I mentioned, this is saying BW for bandwidth equals 5. That looks pretty much the same, right? If I come back here, you can see there's a bit of a bump here that kind of disappears there. And then this is a little smoother on this side too. Here's 4 different bandwidths, right? So this is 0.5, super jaggedy. 2, it looks about like what we started with. 5, a little smoother. And then 10, when we get to 10, it's like almost a normal distribution, right? So now with a bandwidth of 10, we're really not representing our data anymore. Does that make sense? So it's just that, it's again that x-axis, but it's smoothing over them, all right? And it's smoothing relative to a normal distribution. So you have to be careful here. Again, notice the y-axis does change across these. 2 and 5 have the same, but these two are quite different.
Hey, Daniel, I have a question.
Yep.
I guess I get how these vary. I am just a bit confused on like how you choose the optimal one for a specific problem. You're trying to present data to people.
Yeah. So
you might be getting there.
Yeah, well, so that is just a challenge. And that's part of what I'll ask you to do in the lab is look at different bandwidths and decide on what one you think is the best. And, you know, unless you do something like 10 or 0.5, I'm probably not going to argue with you, right? It's sort of a personal preference. The thing is, what you're ideally wanting to do is represent your data, right? So it's not going to be overly smooth like 10, and I would lean more towards 2 than 5 on these, right? But certainly this is way too much, right? It's way too spiky, and this is way too much also. So you're just trying to find a value, and that's why you would explore a couple of different versions of this that is going to smooth your data without misrepresenting your data.
Okay, so more of an art than a science kind of thing.
Yes, for sure.
Okay.
Yep, there's no, I mean, if you are doing an analysis, right? So like in regression discontinuity stuff, I know that there's some things where they want you to do some analysis that helps you figure out the bandwidth for the thing that you're doing, right? And there might be examples like that, but when you're talking about just a visual representation of it, you know, I think you could have 2 different people that look at the same underlying data and choose 2 different bandwidths, and that's fine.
Okay, thank you.
I mean, they'd probably be still in the same ballpark, but probably not exactly the same.
Awesome.
Other questions? Okay, so quickly, we talked about this a little bit, but this is the actual code to do it. We might want to know how well these data represent or approximate a normal distribution, right? So in this case, notice I'm saying sample equals age. So on my x-axis, I have age, right, on all of these. Instead of saying x, though, I'm saying my sample is age. And then I just do stat QQ line, change the color if you want, and then geom QQ. So stat QQ line is going to give me this blue line under here, right? And that is my theoretical quantiles from a normal distribution. And then geom_QQ is going to compute those empirical quantiles. And so now the degree to which these points deviate from that line essentially is how our sample is deviating from a normal distribution. Okay, and this is pretty much as we would probably expect based on looking at it back here, right? It's down in this lower tail where it's really deviating from a normal distribution, right? So that can be helpful as well. This is not one I would use to communicate with people, but it can be a good check for you. All right, continuing with distributions, but now we're going to look at grouped data. So let's say we want to display more than one distribution at a time, right? How do we do that? Probably the most standard approach is to use box plots. And there's nothing inherently wrong with box plots. I think sometimes we as scientists, right, think that people can interpret box plots better than they actually can because we're so used to them and we see them all the time. Whereas like a general public audience might not really get it. They might not really understand what a box plot is. So that's the only real caution there. But if you're using, if you're trying to publish in a scientific article, box plots are fine. They can hide some of the data a little bit. And so violin plots are an alternative. There are other alternatives too. And there's been significant pushback against violin plots also that you should probably be aware of. That's mostly just because of what they can end up looking like, just visually. And then jittered points is another option, right? So rather than showing the distribution and trying to smooth it in any way, you just plot the points. And then jitter just means you're adding some random noise to them. If you're going to do something like this, though, so the code with ggplot is geom_jitter, but I would, by default, right, your jittering is going to jitter the x and the y axis. So in this case, I don't think there's any need to jitter on the y-axis. So I would set that to 0 and then just jitter on the x-axis. Okay, so what I mean by jitter is we're going to just add a little bit of random noise to each data point so that it's not just like a straight line of data, right? But better than that, I think, is to use what are called CINA plots. Okay, and what this is going to do is the same sort of basic idea. It's going to add some randomness to it, but it's going to do it a lot more purposeful. So it's going to basically stack the points as you go up. Okay, so here, right, you can see this is looking like this one is looking a lot more like uniform, whereas this one is stacking out here because there's a lot more points there, right? So it's basically a more purposeful way to actually show each point, but then you're stacking them basically in a way that makes sense. You can also use stacked histograms. Those are not my favorite. I'll show you some examples of why here in just a little bit. And you can do overlapping densities. Overlapping densities, I think, actually can work quite well. I think this is a really good example where they do work very well. You just have to be careful about all the same issues I talked about with a standard density plot, right, with interpretation. But in terms of showing like various distributions and then smoothing them, I think they can be quite effective. Another option is ridgeline density plots. This one has some transparency to it that I would probably get rid of. I don't know why I have it in there, because that can sort of introduce this artifact where this part looks and this part, right? Those are this is one distribution and this is one distribution, but this overlapping part introduces this new color where it can almost look like a new different thing. So I would not have that there. But ridgeline density plots I think are quite nice also, and I'll show you how to produce those. So some quick empirical examples. Box plots, hopefully you should all be aware of how to create these, right? So again, the ease with which, well, not again, but the ease with which we can create these is really going to depend on the data that you have and that you have structured your data correctly, specifically that you have tidied your data, right? So in this case, I have a column for sex and a column for age. That's because of the Titanic data I showed you earlier, right? So those came in that format. But it's very common to have age be like, you know, or you could have like, well, okay, so age could be a categorical variable where you have like 10 to 14 and then 15 to 19 or whatever, and you have a bunch of columns, right? And then you're going to have to pivot that longer and then transform it so that you have a column for age. All right, but once you get there, then you're just going to say, okay, I want sex, which is a categorical variable in this case, right? I want sex on the x-axis and age on the y-axis. All right, and when I do that, then all I have to do is just say geom box plot, because it has a continuous variable on the y-axis, and it has, you know, just what the data in this case are, female, male, which is categorical, right, on the x-axis. And so then it's going to be able to produce that. Violin plots are the exact same. Just instead of saying geom box plot, we're going to say geom violin. And then for jittered points, you're just going to say geom jitter. Okay, here's an example where I am, just like I said before, right? I don't really want to add random noise to the y-axis up and down. I don't want the points to jitter up and down. I want them only to jitter left to right. Okay, so that's where I'll say I want the width to be, in this case, 0.3, and I want the height to be 0. And then geom, or the scenoplot, this is a little bit extra work, not a ton, but basically there's this ggforce package, and so you have to have that installed because it's not part of ggplot directly. Okay, but then you can get these airplane looking things in this case, or trees maybe. All right, questions on any of those before we get going? So basically it's just, you know, these are different ways to show the same thing. Again, as I said before, there's nothing really wrong with box plots, especially if your audience is familiar with them. But these examples are ways to actually show the data. Scenoplots are my favorite of those. They're ways to actually show the data that might communicate the distribution a little bit better than a box plot, and not because it's quite common for things to be hidden by summary statistics, right? And that's essentially what a box plot is doing. Okay, so stacked histograms.
A question, actually.
Yep. Sure.
Yeah, I just wonder about your AES function, the command that, because I generally see in the parentheses, the left one would be an x-axis and on the right one would be a y-axis. But in your Titanic dataset, I only see you use command for the x-axis, but not the y-axis. So I wonder how could like R knows what are the y-axis?
Yeah, so in this case, the reason for density plots and for histograms, I only put my x-axis because it's going to calculate the y-axis for me, right? So I'm putting age along the x-axis, and it's going to calculate the counts for me. So the count is just, if I do geom histogram, it's going to figure out the y-axis for me. And same with geom density. If I use geom density, it knows what's on the x-axis because I tell it that explicitly, but then it's going to figure out the y-axis on its own, right? Whereas when I moved to box plots and these sort of things, then I have to explicitly say, this is what I want on the x-axis and this is what I want on the y-axis.
Okay, got it. Thank you.
Mm-hmm. Other questions? Okay, so for a stacked histogram, this is an example, right, where I'm saying geom histogram, and then all I'm doing is just saying AES now, fill equals sex. All right, so I'm using AES because I'm accessing a variable in my data set. That variable is called sex. Okay, so what it's going to do then is it's going to fill in that histogram with the colors of that variable, whatever they are. Okay, in this case, female, male. So then we end up with a histogram like this that is stacked. I think this is really hard to interpret and really odd, right? I think it's nice for one specific reason, and that's if you want to compare the distribution of male to the total distribution, right? But this is not really female, right? If you want to know the female distribution, that's like almost impossible to interpret there, right? Because it's starting at a different place each time, right? And if you really want to compare, I didn't include it in here because it's quite a bit more complicated, but there's a blog post I can find that let me make a note for myself real quick. If you really want to show that, right, what you can do is you can have like this, the total distribution in the background as like a dark gray, and then overlay the male distribution, and then do that again with the dark gray background in the background, and then overlay the female distribution, right? And then that way you can see each of those distributions relative to the whole, which is better. But the code is quite a bit more complicated, so that's why I didn't include it in here. So you might think, you know, one thing you could do is, instead of doing this, you could say position equals dodge. And what that's going to do is, instead of stacking them, right, this is true for bar plots and for histograms, instead of stacking them, it's just going to place them side by side. Still, I don't think this is particularly good. Dodge does not go in AES, right? Notice, because we're not accessing a variable in our data set. And this is maybe preferable to the last one. I still don't think it's particularly good. It's still quite difficult to see the overall distribution for each of them because now they've got this weird spacing. So what I would recommend instead is just use facet wrap. Okay, so here I've, you know, added a little bit more fanciness. I do have a comma there that shouldn't be there. I'm sort of surprised that ran without problems. But and then I'm just saying plus facet wrap. Okay, and now you can see each distribution. Again, if you wanted to see these distributions relative to the entire distribution, there's a way that you could do that by adding that distribution to the background, right? And I think that would be better than either of the previous alternatives if that's something you're interested in. Okay, does that make sense why you would do this as opposed to that or that? Are there questions on that or objections to what I just said? All right, overlapping densities. So now we're looking at density plots, but looking at them by a group. Okay, so again, just continuing with the same example, we have age on the x-axis. We're not specifying the y-axis because it's a geom density and it's going to figure it out on its own. But then we say fill equals sex. Okay, and notice I am using AES again because I'm accessing that variable. And then one thing I like to do with overlapping densities, certainly not required, but is to say color equals white. And what that's going to do, again, so with all of these, right, the fill is what the entire thing is going to be colored as. And then the color is the outline. All right, so by saying color equals white, it's changing this line right here where they overlap to be white. And so you can kind of see that separation a little bit better. If you're doing overlapping densities, you're almost for sure going to want to include some amount of transparency, because otherwise you won't be able to see both of them. I don't think the default colors work very well here. The default colors in ggplot don't work well generally, I would say, for communication purposes. They're not the best for color blindness and a few other reasons. So you can change those manually if you want. This is an example. I don't know that these really work very well either. I thought they did when I created it, and now they're on the slides and I'm not so sure I buy it. But anyway, what I did here is this is all pretty much the same, and then I'm just going to say scale fill manual. All right, we'll talk more about this stuff when we get to colors. And then we just specify two values. So these are two values that I got from that HSL picker one, one of the ways, I think the way I did this, and one way that tends to work well, is this is the lightness one, right? So you get to a color that you like, and then you're going to drag that down to like 35 for one of them, and then maybe up to like, 85 for the other one or something like that. And then you have the same hue and the same saturation, but just different lightness, okay? Okay, ridgeline density plots. Again, you need another package to do this. So this is going to be the GG Ridges package. I am namespacing here to explicitly show that this is from the GG Ridges package. So if you want to do this, it's not going to work out of the box with ggplot, right? But now we're notice our X and our Y axis are flipped, right? So what we've been doing in the past with box plots and back here, box plots, scenoplots, right? We have our categorical variable on the X axis and our continuous variable on the Y axis. With a ridgeline density plot, we're going to do exactly the opposite, right? We put our continuous variable on the X axis and our categorical variable on the Y axis, okay? And then that allows us to just compare those two. Ridgeline density plots tend to work well when you have a lot of categories. So, like maybe you have like rank or something, and there's like 20 different ranks that you're exploring, right? That it'll work still with like 20 different categories. So that's where I think ridgeline densities can be quite effective.
Hey,
All right.
Daniel.
Yep.
I'm sorry if I maybe don't understand the plot, but how can it go below 0 for this?
That's
like,
a very
below
good point. So it
0?
should not. And that's actually a common problem with density plots generally. And in this case, I just didn't fix it. So that's what it is. But because we're doing that kernel density smoothing, right? Again, where it's taking the raw data and it's smoothing it relative to some distribution. Once it does the smoothing, there's no reason it can't go past 0 because it doesn't know the data, right? It doesn't know that you can't have a negative age. So what you should do, what I should have done here is just truncate that by specifically specifying, the X limit is 0 to whatever.
Okay, that makes sense. Thank you.
Mm-hmm. I'm glad you pointed that out.
Daniel,
Yep.
would the GG Ridge always try to curve our data based on normal distribution, or what kind of distribution they use?
Yeah, so it's not GG Ridges specific, it's density plot specific. And yeah, as far as I know, it's only normal. You can choose different shapes, but I'm not sure if you can choose different distributions. I might be wrong about that. So, we could check into that further. But generally, it's going to smooth relative to some distribution, and all I've seen anyway is normal distributions.
Okay.
Any other questions? All right. These are really cool plots. This I don't think quite shows how neat these plots can be. Again, as I said before, I think they're sort of best when you have a bunch of different categories. So I'll see if I can find an example of that too. So yeah, I'll try to send that out after class. Okay, visualizing amounts. So there's lots of different ways to visualize amounts. Amounts are going to be different than distributions, right? When you have a distribution, you're trying to look at, the shape of the continuous data. In this case, we probably have some categorical variable, and we're looking at how much of each level of the categorical variable we have, right? So bar plots, flipped bars. I tend to actually prefer flipped bars most of the time, not always, but a lot of the time. And dot plots, right? Those are kind of the basic options. So these are all, right, the same thing, basically, just different versions. Dot plots are nice, again, when you have a ton of different levels. So you can just sort of see the cascade of dots versus like overwhelming number of bars. If you only have a couple levels though, bar plots are probably going to be better. And then heat maps. Heat maps are slightly different version of the same thing. They are a little more controversial than the other two, and they are, I think they absolutely have a place. That's my opinion, but some people will think differently and say you shouldn't really be using heat maps. Part of it is because they definitely don't tend to work as well as bar plots. If you can do a bar plot, that's just about the most effective data viz you can do. It's really simple, but it works really well. We're really good at seeing differences on one axis, right? Like differences in size. Whereas a heat map, you're going to be judging differences in color, basically, according to a different variable, which is a lot harder. And you have a lot of people that have color blindness issues. And so it's really not going to work well for them, especially if you don't choose your colors right. Okay. So you're going to have to be much more careful about heat maps. And if you're using heat maps, you might experience some pushback. And that's okay. All right, so we're going to move to a slightly different example for this set of slides, right, for visualizing amounts. I'm using Rio import here, which I don't typically use, but I know you all used it last term. So that's what I'm using here. Notice I'm using the here package, and I'm saying go into the data folder and then get US average tuition.xlsx. Okay, if you've pulled the most recent changes, you should have that data set. Okay. So this is what it looks like, and pretty much immediately to me, I would say I'm going to have to rearrange this data set. I don't think I do that immediately. I think we just look at 1 year, but probably I'm going to want to look at all years together, right? So I'm going to have to rearrange this so I have a column for the year and a column for the tuition dollars. All right, so let's just start out by looking at 2015-16. Okay, the first thing I might want to do is say, all right, let's just put state on the x-axis and then the tuition amount on the y-axis for 2015-16. And then we use geom call. All right, the main difference between geom call and geom bar is, again, that y-axis. If you use geom bar, it's going to try to compute some summary statistic for you. So it'll often do counts, right? But you could also do means or things like that if you want to pass an additional function to it. Most of the time I end up using geom call because I have a variable that I know I want as the y-axis. All right. This is what I'm classifying as the 3 puke emoji version of this plot. This is not a good plot, right? It's impossible to tell what state is which. All right. So this is a 2 puke emoji version. I have made these much smaller, and I've turned them on their side. I know that this is runs off, but you can scroll on that to just see that I said size equals 10. All right. I don't like this because these get very small, and then you kind of have to crane your neck a little bit to see each version of that. All right. So 1 puke emoji version. This is actually not that bad, and it's probably one of the more common versions. Is same thing, right? But now all we're doing is we're just saying plus chord flip. So instead of having all of this theme stuff to get these labels like that, I just say chord flip, and now I have all of my states there, right? And now I can read them like a normal human would without craning my neck, and you can see all of them. The reason I still think this is not very good is because it makes it difficult to say, okay, what is, you know, the relative ranking of these. Like I can probably figure out that either here, Vermont or New Hampshire are probably the two most expensive. So it looks like New Hampshire is the most, and then Vermont. But then the third is going to be probably Indiana, or it's hard to tell, right? It could be one of those three. So instead, I would argue that unless there is a predefined order of these things, right? There's no reason for them to be in this order. This is just alphabetical order, right? So and maybe that is important if you're interested in a specific state and you want to be able to quickly find those different states because alphabetical order makes sense there, right? And so if that's the case, then this is fine. But I would argue in most cases, unless there is like some implicit ordering of these, that you should go ahead and reorder them. So fact reorder state according to the 2015-16 values. And what that's going to do is it's going to basically make this cascading down. All right. So the most expensive is New Hampshire, then Vermont, then Pennsylvania, then New Jersey, etc. Okay. And that way you can very quickly get the relative ranking of the states, and you can pick out any state in here and identify sort of where it is. All right. Again, this might be less ideal if you want to say, where does Oregon rank here, right? Because then you have to just kind of start from the top here and go down until we see there's Oregon, right? And so you have to search a little bit more for an individual state, but the relative ranking, I would argue, is probably more important in most cases. Let's say we want to highlight Oregon though. We're in Oregon, let's do it, right? All we're gonna do in this case is we can say, okay, we're gonna do this fact reorder, just like we did before. So we're reordering the levels of that factor, which is state, right? State is our factor, according to the 2015-16 values. Okay, so we've done that reordering. Now we're gonna apply geom_call. That'll get us this, basically, right? But then I'm gonna call geom_call again, a second time, but I'm gonna switch the data source. And all I'm gonna do is I'm gonna say filter, I'm gonna filter my tuition data set where state equals Oregon, okay? And then I'm just changing the fill on that column, okay? I could also do, like let's say I wanted to do the entire West Coast. I could say where state is equal to Oregon, or state is equal to California, or state is equal to Washington, or you could do, state is in C, Oregon, Washington, California, whatever. But now we end up with something that looks like this, okay? And again, if we're thinking about interactivity, right, there's, you could build something like this in like a Shiny app where this Oregon gets swapped out. So you have like maybe a little button that somebody could push, and it would pick whichever state they wanted, and then that state would pop up highlighted like that, okay? To me, there's still quite a bit we could do here to make this better, but this is a pretty good plot at this point, if our purpose is to show tuition cost and highlight Oregon, right? Because now we see Oregon very quickly. We don't, it's immediate that we see Oregon because of the color change, and we can see its relative ranking in the United States. But it's not always good to sort, right? I said that should be your default if there's no implicit order to it. Things like age do have an order to them. So here's an example where I have sorted, and now it's really much less interpretable, right? I have 45 to 54, 35 to 44, 55 to 64, 25 to 34. That is silly, right? It's much better if we look at it by age, because this has an order to it, right? So now it's going in the correct order, and we can see it's basically a normal distribution. Okay. Questions on any of that? Okay, I'm going to move through the bulk of this really fast that's left, and we probably still won't get through all of it, but because we're running short on time. All right, so let's look at average tuition by year now. So as I mentioned at the start, we're going to have to rearrange this. So I use pivot longer, move it. So now I have a column for year, and I have a column for average tuition. So I'm going to compute summaries. So after I've done that, I'm going to group by year and then just compute the mean tuition. All right. Good. All right. So now I have annual means. This is the data set that I created right here. Just going to put the year on the x-axis and the mean tuition on the y-axis. So you can see we have a pretty steadily increasing tuition. Better, I would argue yes, but you could argue no, right? Whether this is better than this. Part of what I like better about this second one is these labels are much easier to read because they're able to be larger pretty easily. So we just apply chord flip. Better still, maybe, this is now that dot plot version, right? So again, this is kind of just personal preference. Even better, I would argue this now is better. In this case, we've now treated year as a continuous variable, right? And I've done that by just using from the readr package parse number on year. So now the x-axis is a continuous variable, right? And we can see the trend in mean tuition across years. All right. Group data. So now we have the same, we're looking at the same basic thing. Or no, we're not. In this case, we're looking at just 2005-06 and 2015-16. So just 2 years of data for each state, but I'm moving them again so that we have now 2 data points for each state. And then, so I don't know why I called this LT, whatever. So we're going to put state on the x-axis, tuition on the y-axis, and then we're going to group by state, change the color to gray 40, and then add geom point color by year, right? And we end up with something like this. Okay, this is, I think, a quite nice plot as well, because what we're doing is we've got every single state here, right? But then we're showing the change in their tuition from 2005-06 to 2015-16. So the wider that band gets, the more their tuition changed from those 2 years. Okay, these are called dumbbell plots. I think they're pretty nice. All right, so I know we're running super short on time. We only have 3 minutes left, and I know I went through that part really quick, but I just want to show you a few other things. So let's now say we're looking at every single year, right? We could do a heat map. All right, so let me look back at this data set real quick before we get there. So we have year here. So Alabama, 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 right? We have every single year and then the tuition for that year. Same thing then for the next state and the next state and the next state, right? So we have the tuition for every single year. And then what we're going to do when we create a heat map is we're going to put year, our categorical variable, on the x-axis, and state, our other categorical variable, on the y-axis. We then use geom tile, and we use AES because we're accessing a variable in our data set, and we're going to fill by that average tuition. Okay, so now this is hard to see because it's so small, but you can follow a given state across time, and within a given year, you could theoretically look across states. That within a year part is difficult because there's no ordering to it. So that's where I would again use fact reorder state according to average tuition. And now this is, I would argue, a better heat map. All right. So what we've done now is, right, basically this is the cheapest and this is the most expensive. So you can follow across for one given state and you can look within a given year as well. Okay. Even better, you could change the color scheme. So this is the magma option from the Veritas color palette. There's a bunch of these. One of the ones that I think works quite well is there's like a purple green one as well. If you don't like Veritas, that's fine. But the point is you should be exploring other color palettes, and we'll talk about color quite a bit in a little bit. We have a whole week on it, right? But different color palettes can help you see differences much stronger. So this is like maybe a final product that you would end up sharing in some sort of medium, right? All right. Last thing, you could also, because these are geographic data, right, you could go ahead and actually just show them by state, right? In this case, I would have to actually join them with geographic data, which is what I did in the previous slides that I just skipped over. But now you can look at a map of the United States for every year and see how they change. You could even animate it, right? So this is with GG Animate. The thing that I think is interesting about this is just seeing Wyoming be this hole of darkness, right? It just never changes. So, but you can see, they're all pretty much getting brighter. So they're getting more expensive, and then they drop back down. So, okay. So we've got a lot a long ways to go. Today was just an introduction. Towards the end there, in particular, it was very quick. We didn't really even talk about multivariate data except, like categorical X and continuous Y. So we'll talk about a lot more from here, but this is just, quick introduction. Hopefully at least the start of it was review. And next time we will have a lab where we'll do Git and GitHub collaboration. I'll be asking you to create branches and then merge those branches, right? It must be completed as a group, as I mentioned, and the actual lab itself, you can look at it, but it's basically create a plot and then style that plot, and then create a different plot and style that plot. And it's using some of these things that we're just looking at.